All right, our next speaker of the session is Shira Chapman from Ben Gurion, who will tell us about holographic complexity of de Sitter space.
So, hi everyone. I would like to start by thanking the organizers for giving me the opportunity to present my work in this conference. And as you can see, the title of my talk is Holographic Complexity and de Sitter space. But as you'll see, my goal is a bit more general. I will try to answer the question, can we use holography, in particular with tools from quantum information, to probe the de Sitter horizon? The talk will be based on a paper together with Eric David Kramer from Machon Lev and Damian Galante from King's College in London, and on some work in progress together with my postdoc Stefano Baiguera and my student Rotem Berman. Stefano will be presenting a poster in the poster session later on today, so I encourage you all to go and have a look. So as I said, my goal is to answer the question, can we use holography together with tools from the world of quantum information to study some properties of the de Sitter horizon? And in this talk, I'm going to focus on two different approaches to try and answer this question. The first approach, often referred to as center geometries, or flow geometries, are essentially the idea of embedding a de Sitter bubble into an ADS space, and in such a way have a dual theory on the asymptotic boundary. And the second approach is the idea to study a holographic theory with finite number of degrees of freedom, living on a holographic screen at the boundary of the static patch. So that's holography at the stretched horizon. And I will essentially use these two approaches together with tools from quantum information, in particular holographic complexity, to try and see what we can tell about the dual theory. All right. So before I delve into the details, let me do a very brief recap of some basic facts about de Sitter space. So de Sitter space is a maximally symmetric solution to Einstein's equations with a positive cosmological constant. And it's important because it describes both the early universe during inflation and its far future, but to a good degree of approximation already the world in which we live. That's the metric of de Sitter space. And the Penrose diagram is essentially a square, where, as you can see, the red lines are lines of constant radial coordinate, the blue lines are lines of constant time coordinates, and we live here. That's r equals to 0. That's the horizon, the cosmological horizon, and that's future infinity. And this triangle over here, bounded by the cosmological horizon, is very often referred to as the static patch. I should say that r equals 0, despite looking like a boundary in the figure, is not really a boundary. It's like the place where the sphere shrinks to 0. And so essentially we have the problem of not having a temporal boundary, a time-like boundary to work with. All right, so since I told you I was going to do holography in de Sitter space, I should answer two questions. Why would I want to do holography in de Sitter space, and why is that hard? So why would I want to do it? I think the reason is pretty obvious. We hope to extend the success it had in anti-de Sitter space in various contexts. And why is it hard? So I already said, essentially we don't have an asymptotic time-like boundary within the static patch where we can put the field theory. But despite this difficulty, different approaches were put together to try and do holography in de Sitter space. I think the most famous one is the idea of placing some sort of Euclidean CFT at future infinity and studying its correlators. Of course, this approach has some problems, in particular that there is no time direction over there and that future infinity is not accessible to the observer in the static patch. The two approaches I will focus on today are the idea to embed a bubble of de Sitter space inside anti-de Sitter, and the idea of placing holography at the stretched horizon, which correlates with the idea of having de Sitter represented by quantum mechanical models with finite number of degrees of freedom. And of course, there are many additional approaches. I'm not listing them all. All right, so let me take a look at the first approach and explore holographic complexity in flow geometries or centaur geometries. So what is the idea? Here, as I said, to embed a portion of the sitter inside ADS. And this was attempted in the past, but it was always found that the inflating region, and in particular the de Sitter horizon, is always hidden behind the horizon of a black hole from the ADS boundary, as you can see in the figure. And the main obstruction to having access to the inflating region from the ADS boundary is essentially a consequence of the null energy condition together with focusing equation, which essentially tells us that a congruence of null geodesics leaving the ADS boundary can't converge and then diverge again. But to these obstructions, there are in fact loopholes. These were discovered rather recently in the past couple of years, and they were eventually used to construct geometries in which the inflating region is in fact accessible from the ADS boundaries. So let me give some examples of such loopholes. So in particular, in two-dimensional geometries, we don't have a sphere, so all this like focusing and defocusing is not a problem. And so in this case, you can definitely embed a de Sitter 2 patch inside ADS2. That's the setup that I will focus on today, but I wanted to emphasize that that's not something special to two dimensions. So, for instance, in 4 dimensions, you could embed a de Sitter 4 type space into a larger, not ADS4, but ADS2 cross a sphere with some very slowly varying size of the sphere in a like the sphere doesn't change in the conventional way. And perhaps you might be confused because you were expecting to embed DS4 inside ADS4, but remember that what we want to do is actually study the de Sitter horizon. We don't actually choose which theory it's embedded in, and the fact that there is always some kind of ADS2 factor at the boundary is perhaps natural from the point of view of these ideas of de Sitter having a finite number of degrees of freedom or being dual to a quantum mechanical model. All right, I will, as I said, I will focus on the two-dimensional case, and let me tell you a little bit more about how those geometries look. So these are solutions to two-dimensional dilaton gravity with a piecewise potential, which is with a negative slope for certain values of the dilaton and with a positive slope for higher values of the dilaton. And essentially, the slope of the dilaton potential is what determines the curvature of space. So it's essentially inversely proportional to it's proportional to minus the Ricci scalar. So this geometry exactly will be de Sitter below a certain value of the radial coordinate and ADS above this value. And the metric is just as you would expect. So essentially a two-dimensional metric, which looks like de Sitter space below a certain value of the radial coordinate and anti-de Sitter space above it. And as you can see in this Penrose diagram, essentially we have embedded the de Sitter bubble inside ADS in this way. So the de Sitter is in the infrared, the ADS2 is in the UV. As usual with all these setups, the ADS2 space caps off at some constant value of the dilaton. That's not the same value where we glue the DS and ADS. And for the calculations of complexity that I will present in a second, we use essentially a sharp transition between de Sitter and ADS. This sharp transition doesn't make much difference. I will actually talk about that. All right. Complexity. So I said I'm going to compute complexities in those geometries. Complexity is essentially the minimal number of operations which are required to construct a quantum state. And in the context of holography, some proposals were made for what complexity might be dual to. One of those is the idea that complexity is dual to the volume of an extremal slice, which anchors at the boundary where the state is defined. So before I go on to tell you how complexity looks for centaur geometries, let me remind you how it looks for anti-de Sitter, for black holes in ADS2. So essentially in this case, the geodesics are very simple, or the maximal volume slice, since it's 2 dimensions, and they are simply straight lines. And there is a very simple formula, which at least when the ADS boundary is far away, describes the time evolution of the length as time progresses on the boundary in a symmetric way. And that's essentially the formula, log of a cosh. If we consider late times in particular, we see a linearly increasing value for this length of the slice. And this was proposed or related very often to the chaotic nature of the theory. One more thing which is going to be useful before we move to the centaurs is to talk about geodesics in DS2. So I think that's maybe not just to mention, these don't have a complexity interpretation, but just to see how they look. And I think maybe it's not that well-known fact, but essentially geodesics in de Sitter don't exist between any 2 points on the world line of an observer, any 2 symmetric points, but just between points which are at inverse times, let's say. So when symmetric, only at t equals 0. And essentially there is not a single geodesic, but a whole family of them, and they all have an equal length of pi. All right, so finally going back to the centaur geometries, the geodesics have the form that you can see over here on the left. They have some peculiar features that I will mention now. For instance, geodesics starting at very early times will go behind the future horizons, while those at very late times will go behind the past horizon. You can also identify in the center of the centaur this kind of de Sitter diamond type of multiplicity of geodesics going between the 2 same points. And the length of the geodesics for quite a long range of time is given by the following formula, which is very similar to the one that we had in ADS, but instead of a cosh, we have a cosine. And so, as you see, instead of increasing, in this case, the complexity is decreasing. One more rather peculiar feature is that the geodesics actually stop existing at a large enough value of the time, essentially when they are connected by null lines from the de Sitter region to the ADS boundary. And this is reminiscent of the fact that in de Sitter, not every 2 points on the world line are connected by geodesics. So what should I make of that? So as I said, geodesics don't grow linearly with time. In fact, they decrease, and they only exist for times of order the inverse temperature. So what should I make of that in the context of complexity? This is somewhat unclear, but I'm going to mention some possible proposals. So I think the biggest question in this context is what to make of this time at which the geodesics stop existing. And there are several proposals. So the first one, proposed by the group at Perimeter Institute when studying complexity in de Sitter, is that one should actually chop off. What's the reason that we stop having geodesics is that essentially they fall into future infinity. But the proposal is to place a cutoff there. What is this cutoff is not extremely clear. Perhaps a cutoff for the Euclidean theory living at Scri+. But the proposal is then to consider an additional branch of geodesics which are piecewise, which go along the cutoff at Scri+. In this case, the complexity will actually grow linearly. So these geodesics will win. They will be the longest ones. And essentially, complexity will just grow linearly at a rate dictated by the cutoff. And this relates well with the hyper-fast scrambling ideas of the group at Stanford. But of course, this just trades the question that we had before about the strange behavior of the geodesics. with a new question of what exactly is this cutoff at Scri+. Another option is to analytically continue the space to complex values, and upon this analytic continuation, the lengths become complex. In the context of complexity, it's not extremely clear what it means, but let me mention a fact that to me looks perhaps related, is that the proposal exists that these central geometries are actually consistent with SYKs with a complex deformation. And so if we take this proposal seriously, we would have to redefine complexity in such systems, and that perhaps could account for this complex behavior of the geodesics. But another option is just to take it seriously and essentially say that the decrease in complexity seems to indicate that the dual theory is in fact not chaotic. And that is not the only indication, in fact, that the dual theory to central geometry is not chaotic. There are additional indications, in particular from the behavior of the out-of-time ordered correlation function, which oscillate rather than having some kind of exponential behavior, as well as some behavior of the quasi-normal modes in this space. Now, you might be worried that this kind of peculiar behavior which I'm seeing is due to this funny sharp gluing between DS and ADS, and perhaps it will disappear if I smooth out this sharp gluing. And the answer is that that's not really the reason. And so to see that, we did a number of additional tests. In particular, we looked at gluing larger or smaller portions of the Sitter2 space to ADS. This you can see in the Penrose diagrams over here. And in all these cases, the complexity simply decreases and stops existing at a certain time. On the other hand, if you do sharp type of transitions between two anti-de Sitter spaces with different cosmological constant, you would always see a linear increase in the usual way that we see in anti-de Sitter space, dictated by the size of the horizon. And of course, all these results raise the question of what happens in higher dimensional cases. This kind of a fluke of 2 dimensions. Would it look the same in higher dimensions? And very recently, these 4-dimensional flow geometries were constructed, and so we hope to be able to look at them as well. All right, so let me move to the second approach. The second approach is the idea of placing a holographic theory on a screen near the Sitter horizon. This is this is essentially the idea that a holographic theory with a finite number of degrees of freedom, perhaps a double-scaled SYK, can be associated with the stretched horizon. That is a holographic screen living extremely close to the de Sitter horizon. And roughly speaking, this is the idea that the holographic degrees of freedom should always be placed at a surface with a maximal area within the region which we have access to. So for ADS, this is the boundary, because it's large enough to encode all the information, and in the Sitter, it's the cosmological horizon, because all the directions are flipped. One of the big drawbacks, probably you guessed it already, of this approach is that gravity doesn't really decouple. This is just living in the gravitational region, so it's not really clear what kind of theory should live there. Perhaps an SYK coupled to gravity, we don't quite know. But nevertheless, several groups have taken this approach and suggested that the theory on the stretched horizon has some properties. It was suggested that it's hyperfast scrambling, meaning that it's some type of SYK with a Hamiltonian term that acts on many fermions at a time. And some of its properties in particular, which were noted, is that complexity diverges at some finite critical time and then was proposed to be regularized by this kind of cutoff at future infinity. So how can we test if the theory at the stretched horizon is hyper-fast scrambling or fast scrambling, or what are its properties? In the context of holographic complexity, the scrambling properties are usually diagnosed by considering the reaction to perturbations, for instance, shock waves in the case of black holes. And the idea is one, essentially consider the observable complexity in the presence of a shock wave, as you can see in the diagram over here on the right. The shock wave's in red and the volumes are in green. And the state on the boundary essentially depend on various times, on the right time and on a left time, as well as on the time in which we sent the shock, which we call TW. And in particular, for a symmetric configuration, there is one characteristic feature that one can see in complexity, well, not just one, but one that we studied, is that the complexity starts growing linearly, but only after some very long plateau, and the length of the plateau depends both on the time at which the perturbation was sent and on the scrambling time, which is essentially logarithmic in the relative size of the perturbation. Right, so essentially just looking at this feature is perhaps a way to diagnose the scrambling time of the system. So essentially we wanted to do the same for the zeta, shocks in the zeta. Shocks in the zeta space are actually quite different from shocks in anti-de Sitter space. In particular, positive energy shock waves push the horizon away and make more space available to the observer. Since we throw some mass away, we know less, so the entropy increases. And this is very different from what happens for anti-de Sitter black holes, where this is only possible for negative energy shock waves. In any event, I'm going to focus on 3 dimensions, but we also have results in higher dimensions which essentially all show the same features. And the metric essentially is before a certain time, there is a mass at the origin, and then after a certain time, this mass is thrown away, and we are left with empty de Sitter space. And essentially what we wanted to ask is how does the complexity of the theory at the stretched horizon, or this, I don't know, conjecture theory at the stretched horizon, reacts to the shock wave. And the way to do that is to anchor the complexity of observables, for instance, the volume or the action, just anchor them at the stretched horizon. And additionally, we were following this idea of putting a cutoff at scribe plus. So I will show you results from one of these holographic proposals that complexity is equal to the space-time volume of the Wheeler-DeWitt patch. These are preliminary results in 3 dimensions, but a similar behavior in higher dimensions happens too. So what do we see? We see that the complexity grows linearly after a certain initial plateau. And the linear growth is governed by the cutoff at scribe plus, essentially resonating with those idea of the hyperfast scrambling. As for the size of the plateau, I told you that from the size of the plateau, I can diagnose the scrambling time. So we were able to fit, so that's the size of the plateau as a function of the time of the perturbation and for various values of the relative size of the perturbation, the energy of the shock. And what we see is actually a behavior very similar to the one that one sees in black hole. So essentially dependence on the time of the perturbation and a logarithmic dependence on the energy of the shock. And some additional factors which depend on the location of the stretched horizon. And so that's actually a way to identify the scrambling time. So what we see is actually the usual scrambling time for fast scrambling systems. And as I said, in higher dimensions or with other types of shocks, for instance, from Schwarzschild de Sitter to Schwarzschild de Sitter, we see similar results. And it seems that this is some sort of universal geometric property of horizon. So this raises the question of, can we actually prove this? I'll just say a word of caution. The identification of the scrambling time seems very dependent on the notion of time on the, I'm almost done, on the stretched horizon. And if we used, for instance, the proper time over there, perhaps we'd get some blue shift factors which could reduce the scrambling time. All right, so let me summarize. So we saw that essentially there is a revival of de Sitter holography with different approaches on the market. and that it might be interesting to explore them from a quantum information kind of lens. We talked about centaur geometry, which have access to a theory on a time-like boundary. In this case, complexity from the volume proposal initially decreased and then stopped existing after a certain time. And we proposed a number of different interpretations for that. We also talked about the idea of defining complexity of a theory at the stretched horizon with shock waves. And in this case, it looked like the scrambling time indicated chaotic behavior. And of course, this leaves us with a number of open questions, such as mostly about the quantum field theory interpretation of these two geometries, and what can we say in higher dimensions? Is the theory dual to de Sitter space chaotic, and can we use these holographic setups to answer basic questions about quantum gravity in de Sitter? So as you see, there's lots to explore, and thanks for listening.
We have time for a couple of questions. There's one here.
Yeah, so as we heard in the last talk, the largest entropy state is the one, for a fixed cosmological constant in de Sitter, is the one that's empty de Sitter. So wouldn't one somehow expect, naively, that maybe the complexity should indeed decrease naturally, so that, you know,
sorry,
de Sitter...
I didn't hear your question very well. Can you say?
I was just repeating the observation that de Sitter, pure de Sitter, has the largest entropy at fixed cosmological constant from, you know, excited de Sitter.
Right.
So that you might expect that maybe, I mean, if one buys into this, that complexity should actually decrease as stuff sort of, because, you know, it evolves to the most entropic configuration, but that means just the simplest, you know, maximally symmetric state. So I was just wondering whether that could be a possible narrative.
Yeah, but let me just reiterate. So this kind of decrease of complexity that you see in the centaur geometry, the thing that you have inside is essentially empty de Sitter space. So I'm not sure. I mean, yeah. Perhaps, yeah. I'm not sure that this would be valid there.
There's another question here.
Yeah, thanks for the talk. I was wondering, with this infinite number of proposals for complexity, have you thought about what would happen if, I guess you expect that it is still decreasing in the usual centaur geometry when just the complexity, but have you thought about if they reduce to the same thing in these special cases or in something like that?
If they reduce
to the same type of complexity?
Sorry, can you?
Okay.
Yeah.
Thanks.
Thanks.
Yeah. Have you thought with this infinite number of proposals for complexity if they reduce to the same thing at the end?
Oh, you mean the complexity equals anything kind of stories? Mm-hmm. No, I don't know. So I believe that, I mean, it seems to be quite a universal geometric property of horizons, and you know, essentially, so if we take the two most famous proposals, for instance, the volume and the action, or the volume and the space-time volume, you can look at this Wheeler-DeWitt patch as essentially, you know, a collection of volume geodesics, and so I believe that essentially I believe that all these proposals would give the same, but that would require some testing.
All right, looks like we're out of time. Thank you, Shira.